In this SATSOFT how-to video, we'll illustrate how to compare two patterns by using the so-called delta pattern. As delta pattern is most easily explained and illustrated using a concrete example, we consider here a case with two shaped reflector antennas that was set up and analyzed in a previous video. Both antenna 1 and antenna 2 have been shaped to give a contoured beam over the continental US or CONUS. Antenna 1 has been shaped with no other goal than to maximize the copolar directivity over CONUS, and pattern contours for this antenna are shown here. We can see that its edge of coverage contour is 31.34 dBi, while the level over the northern part of South America is around 10 dBi. Antenna 2 has been shaped to simultaneously maximize the copolar directivity over CONUS and suppress it over South America. We can see that its edge of coverage contour is 30.61 dBi, that is, slightly lower than that of antenna 1. We also observe that its level over the northern part of South America is below 0 dBi, and this is much smaller than the similar levels here for antenna 1. By switching back to antenna 1, we can visually compare the two antennas. This is one way of comparing two antennas patterns inside SATSOFT. But here we will use the delta pattern to compare the two patterns more directly. Delta pattern computes the dB difference between two beams inside SATSOFT, and we'll see that it can be visualized on the map and in performance tables. A delta pattern can be set up in two different ways. By right-clicking on one of the involved antennas and going to New Delta Pattern, or by highlighting one of the involved antennas in the project tree and clicking on the delta pattern icon in the top menu. This opens the delta pattern selection dialog. Here, the beam to form the delta pattern must be selected. The left column in this dialog is locked to the antenna that was highlighted to open the dialog. Any component or composite beam from this antenna can be selected. In the right column, any other beam in the project can be selected. Here we select the composite beam 1 from antenna 1 and composite beam 1 from antenna 2. At the bottom, we change pattern cut polygon to no polygon and press OK. This creates a new satellite in the project tree, and the delta pattern object appears as a child object under this satellite. Selected contours of the delta pattern are displayed on the map. The delta pattern is, because we set pattern cut polygon to no polygon, defined everywhere on Earth where the two source beams are defined, which in this particular example is everywhere on the visible part of the Earth. We would like to customize the displayed contours. This is done by right-clicking on the map and selecting composite contours. We generate levels from -2.5 dB to +1.5 dB in steps of 1/10 of a dB. We fill the contours and change the font size to 12 and click OK. We now see these filled contours on the map. In this example, we're interested in the delta pattern over CONUS. But because the delta pattern is the dB difference between the two antenna patterns, difference values of similar levels as over CONUS appear far away from CONUS, where the antenna patterns obviously have much lower absolute levels. In some situation, as this one, this may produce plots that are a bit difficult to look at and interpret. Therefore, we'll set up a similar delta pattern in a slightly different way. We open again the delta pattern selection dialog and select the composite beams from antenna 1 and antenna 2. But this time, we keep pattern cut polygon to CONUS and leave oversize factor at 15% and press OK. This creates a new delta pattern, as can be seen in the project tree, and selected contours are shown on the map. However, these contours only appear in a region around CONUS because we filtered the delta pattern with the oversized CONUS polygon when generating it. We would like to reuse the contour level and display settings that we set up for the first delta pattern. Therefore, we go to the view and open the Composite Contours dialog. Here we click on Apply to Antennas, select the newly created delta pattern and press Apply. Now the same delta pattern is shown, but focused around corners that we're interested in here. We zoom in on corners to inspect visually the delta pattern. Positive values corresponds to places where antenna 1, which had no suppression goals over South America, gives a higher copolar directivity. Negative values, on the other hand, are where antenna 2 gives a higher directivity. So in other words, the blue regions are where the copolar directivity is lost because of the additional South America suppression goal for antenna 2, while the red-orange region is where copolar directivity is gained in addition to this suppression. The contours provide a visual representation of the delta pattern. As for antennas, it's also possible to add cities and create performance tables for delta patterns. To this end, we first add US cities by opening the Map and Cities dialog and then going to the Cities tab to add all US cities from the database. We see that the cities are then added to the map. Next, we create a performance table for the delta pattern object and open it. In the performance table, delta pattern values are displayed for the US cities. By left-clicking the last column, we can sort the table in descending order and thus see which cities have the largest directivity decrease due to the South America suppression goals introduced to antenna 2. I hope you enjoyed watching this video, and I invite you to see more tutorials on our YouTube channel.